Hey there. So this is the beginning of Lab 9 and 10. Sorry, Lab 10. But before we start, I'm actually going to talk a little bit about AWS. Some people are having problems where their clusters were not being terminated properly, and then they were going into the interface, to the web interface or the AWS console, and they weren't seeing any clusters there, so they thought it was actually terminated. So the problem here is that it seems by default, AWS assigns you to the West Coast region. So if you look at the upper right corner of your AWS console, you see that it shows Oregon by default. However, the script that we created and all the instructions, they assume that you're using the East Coast clusters. And that's for performance reasons. It's just much faster, of course, to use the clusters that are close to you. So if it is set to Oregon, as it is by default, and I go to EMR, which is, if you look, no, sorry. For some reason, it actually went before I did. And if you look at EMR, which is where your cluster would be listed normally, if I click on that, you see that it shows nothing. Basically, it takes me to the screen, which shows up if you don't have any, if you never created any clusters. A lot of people were assuming that that meant that they didn't have any clusters running, which is not true. So the idea is, once you're in this page, in just the landing page for the AWS console, you should switch up here from Oregon to North Virginia, so US East. Everything else looks the same. The only thing that changes up here. But then when I go down to EMR again, I will see all the clusters that I created in the past. And well, they should either, well, hopefully they're not like this. There should be saying terminated user request. Right? If they're not like that, what you would have to do is click on the cluster that you're trying to terminate, and then click the terminate button. Now, it doesn't work over here because I don't have any running clusters, but that button would actually not be grayed out if you had any, if the cluster you selected was running. And that's it. Once you click on that button, that's going to terminate, and you're not going to be charged anymore for that. Please remember that you need to terminate your clusters. I told you, I told my session this a bunch of times, and if you don't terminate, you're going to get charged. And for each cluster, there were very high charges, close to $100 for running probably more than one cluster at once. But turn it off, especially if you don't have credits. And actually, that's another point that I wanted to make really quick. Another thing that you should probably check is if you click on your name, again on the upper right side, and go to Bill and Cost. On the left side, in the left menu, there's going to be a credits function, and this is another account. So this is showing an account that actually doesn't have any credit. If you did have any credits, it would just show a little line over here, a little table actually, with the how many credits, how much credit you have left, and everything. But cool, that was it. I just wanted to again remind you guys. First thing, if you have a cluster, if you created the cluster and you didn't follow the full instructions up to the end of the notebook, or even if you did, just to be sure, go into the console. Open, make sure that you're looking at US East, because your cluster, if you followed our instructions, is always going to be created on US East. Click on EMR, and make sure that they also say terminated. And that's it. So now Raul's going to take over and talk about his stuff. Let me log out.
Okay, so let me find this. Let me know when. Okay, so this lab is on the Back-of-Words model for text analysis and on naive Bayes, and maybe it's just a little bit of clustering since Verena's going to be doing clustering starting next week. Okay, so we're really going to, we looked, when we were doing the Bayesian labs last time, we looked a little bit into the naive Bayes stuff, and we did it with a Gaussian naive Bayes model. That was on diabetes data. But here we want to talk about text. So this is a data set from homework 2 years back, which has data from Rotten Tomatoes, and it has a fresh or not fresh, and a bunch of reviews inside this quote from sort of well-known critics. So we'll just explore the data a little bit. There are about 15,000 reviews, 623 critics, and 1,900 movies in this data. And we can plot a histogram of the average rating per critic. But all of this is not really the important stuff we want to do. We want to look at the quotes. That is, you want to look at the stuff inside of here. So ingenious in concept, design and execution, blah, blah, blah. OK. So the first thing we need to figure out is how we're going to represent this text as data. And to represent this text as data, we use what's called a vector space model. And the idea is really simple. We define the vector derived from the document by a vector v-bar. And to construct this vector v-bar, we basically do something really simple. So consider the document hello world world over here. It has two words in it, the words hello and the words world. And maybe you have many other documents. And all of these documents have some of these words and some other words. So maybe there's a foo and there's a bar and there's a happy and there's a sad and so on and so forth. So the first thing you do is you take all the words you have in all the documents. And you find the unique words in all the documents, and then you assign them an index. So this index is basically sort of like telling you what unit vector that word corresponds to. So now what you're doing is you're considering a huge dimensional space, where each dimension basically is one word. So for example, something like this has 2 units in the world dimension and 1 unit in the hello dimension. And so when you do this, any document is basically represented by a vector in this space. You know, if world comes twice, then you have 2 units in the direction of world, 1 unit in the direction of hello, and if there's something else, then it'll be so many units in that direction. And now you realize that once you have a vector in a vector space, you can think of like multiple vectors in this way in this vector space, and you can see how close these vectors are to each other, what their cosine product is to get similarity, and all these kinds of things. And we'll actually write it in what is called this bag of words format over here. And so what this is saying is that suppose hello was at index 5 in the vocabulary, and world was at index 99 in the vocabulary. World came twice, hello came once, so I'll write it like this. It's a rather sort of like sparse representation of this vector. It's basically saying that the unit vector number 5, and it had the coefficient of 1, the unit vector number 99 had a coefficient of 2. That's it. It's a very simple form. Any document can be put into it. OK, so then once you do that, then a set of documents becomes, in the usual sklearn style, basically a set of vectors, right? And this is what we're familiar with. The usual sklearn style is features and samples. Right? And so you have one vector here, one vector here, one vector here, one vector here, one vector here. Now we are writing it in the sparse representation, right, of this kind, 5, 1, 99, 2. But you can conceptually think of it as saying that in the 5th place I have a 1, in the 99th place I have a 2, and I have zeros elsewhere. And then so on and so forth to the next document, and the next document, and the next document. So this kind of representation is familiar to you from what you've done so far. So here's another example. It's from the book I talked about. It's a rather good book, worth reading. And I think this is from some classical books, like Wuthering Heights and all. And then there are 3 terms here: affection, jealous, and gossip, essentially. And I think that's Sense and Sensibility, Pride and Prejudice, and Wuthering Heights. And it's showing you the frequency of these words, telling you that Sense and Sensibility seems to be an altogether more romantic book. Well, maybe not. I don't know. It depends upon the ratios, right? So this is sort of like transposed from this scikit-learn style, but you get the idea that this is the sort of like term document matrix. So there are some transformations which are done. I mean, if you go and look at Wuthering Heights or Sense and Sensibility, the term affection is probably not just used as affection. It could be used as affectionately. It could be used, or jealous could be jealousy. Gossip could be gossiping. And what we want to do is, if you have gossip and gossiping, there are certain applications in which we might want to consider them both to be the same word, have the same meaning. And so we'll basically stem gossiping down to gossip. And we can also use lemmatization, which also reduces words to lemmas, like work, working, worked would all reduce to work. So there are these different sort of like processes that you can undergo. You can even go even further. If there's a whole bunch of synonyms for work, right, then you can have all of those synonyms reduced down to work so that you have a more kind of semantic representation of the document. So it depends on what your application is. One of the other things we typically tend to do is to remove stop words from our vocabulary. So common words such as the, at, am, and, all of those, you just remove those. And we might actually want to be even more specific. We could just look for particular parts of speech such as adjectives, and you'll be doing this on your homework. And this is often done in sentiment analysis because adjectives sort of like, give you a kind of notion of comparative and superlative and so on and so forth. Okay. So this again is basically the kind of the kind of picture that if I have two documents, D1 and D2, I can look at the similarity by getting the cosine of the angle between them. Kind of similar to the Pearson correlation that you did in homework 4, but this is like the cosine similarity. But the fun part of this is that you can also kind of make a query. So consider the query Q is equal to jealous and gossip. So this query then turns into this sort of unit vector on the 3 coordinates below. And now you can take its dot product with the appropriate document and see which documents have the highest dot product and return those. So voila, you just written a search engine really fast. It's not the smartest search engine, but it may be good for certain applications. Okay. So let's look what some of this looks like in code. The key thing from scikit-learn is the count vectorizer, and what the count vectorizer does is basically it takes a bunch of documents and it converts them into these vectors, and it just does exactly what you saw here. It basically writes it with the counts. So here's some text: hop on pop, hop off pop, hop hop hop, and that's the original text. And we're going to do a count vectorizer, and we're going to do a count vectorizer with min df equal to 0, and I'll just come to what the min df is in a second. And then we're just going to call it the usual scikit-learn style. We're going to do we can do vectorizer.fit. But we can also do vectorizer.transform after having done the fit, or you can combine them together using fit_transform, right? You've seen this before when we did the standard scalar. It's exactly the same thing. And we'll convert it to a normal array because it stores it in a sparse array, because these arrays are really, really sparse. And we can get the feature names. So the original text is hop on pop, hop off pop, hop hop hop. The transform text vector is 1 0 1 1. So you can see the matrix the way it came up. Basically, the first one is sort of like hop over here, and this is the key I'm looking at. The first one is hop. The second one is off, on, and pop, and there's no off, on, and pop in this, but this one has on and pop, so it's 1 and 1 there. So that's what it looks like. So that's your set of documents. So that first document is this, second is this, third is this. So that's in code what we were talking about a little bit earlier. Okay. So we're going to write a little function which is called makeXY, which basically takes stuff from this critics frame and gets the quotes out. And it runs, it creates a count vectorizer with no arguments if you don't give it the vectorizer as an argument coming in. It creates a fit transform of the critics quote over here. So it takes the quote, and it basically actually going to take each and every one of the quotes, and it's going to transform it into this X feature matrix over here. And we're storing it in a particular sparse format over here. And just for, because we're going to actually do a naive Bayes classifier now, we are going to also see which ones of these were fresh and give them the value 1. So we can do that on the entire data frame over here. Now naive Bayes, just to remind you what naive Bayes is, basically, you are using Bayes' theorem, which says the probability of a class given a document is proportional to the probability of the document given the class times the prior probability of the class. And that the fundamental naive Bayes assumption is this, that the probability of the document given the class is the product of the individual terms given the class. And so you can see basically that that's what we're doing here. And there are two things you need to do whenever you write a whenever you write a naive-Bayes classifier. First, work in log space. The reason to work in log space is that these probabilities are extremely small, and you can get underflow errors when you multiply this probability together. So work in log space. In fact, the scikit-learn naive-Bayes classifier will only output probabilities, and I think it only outputs probabilities, these class conditional probabilities, in log form for you. Don't quote me on that, but I suspect that is the case. But you must also handle non-existent terms, as we talked about last time as well. And there are sometimes terms that are not going to be there in a document, but they are there in your vocabulary. What you do is you simply hallucinate a Laplace estimate for it, and that's what that estimate is. It has this regularization alpha, basically. Okay. So let's do it. We're going to use multinomial naive-Bayes, and multinomial naive-Bayes uses the multinomial distribution, which is the generalization of the binomial distribution. And it's multinomial because you have this kind of choice of multiple words that goes in a document. So as Joe was talking about in class this last Thursday, basically naive-Bayes is a generative classifier. It basically gives you a generating process for the document. So it first, based on the prior probabilities, the first thing it does is that it flips a coin, which says, is this a positive document or a negative document? Is this a fresh review or is this a rotten review? Okay. Once it's done that, it flips this coin, which basically says for each given word, what's the probability of that term given that particular class? So it flips that coin and it emits a term. It flips the coin and emits another term. It flips the coin and emits, and it goes through the entire vocabulary, and based on that it flips. And for each vocabulary there's a different probability, and it flips the coin based on that probability and emits it. And if you restrict your document to be 10, then it can only do this 10 times. So that's the sort of generative process for naive-Bayes. And here we actually code it up. And you get multinomial nb.fit of x train, y train over here. Here's a train test split. And you look at the accuracy, and you get a 76% accuracy on the test set when you do that. And you can look at the training accuracy and the test accuracy, and notice that this by default, this is a fairly overfit classifier, where the training data is at 0.92 and the test data is at 0.77. So clearly, we haven't done any cross-validation. We haven't picked out any parameters. The only parameter, in fact, we've identified so far is this alpha. But it's not really the only parameter in this problem, and we shall see why in a second. So to do this entire process, there's two parts in it. The first part is a convectorizer, where we actually converted the documents to these words. There are some parameters for the convectorizer, and I'll come to one of them in a second. And then the second part of this is, after doing the convectorization, is to actually do the naive-Bayes classifier. And now the problem with this whole thing is your vocabulary depends upon this convectorizer, and it actually depends on what parameters you put into it. So the critical parameter we are talking about here is something called MinDF, and I've just included over here the output from the scikit-learn webpage describing the convectorizer. And so MinDF it says that when building the vocabulary, ignore terms that have a document frequency strictly lower than the given threshold. This is also called the cutoff. If the parameter represents a proportion of documents, if it's a floating point, it represents a proportion if integers are absolute counts. So for example, if I say 5 over here, that's saying that that particular term should have a document frequency of 5, which means that there should be at least 5 documents with that term in it. And if not, I'm not going to even take that term into account. So that's why you need this you need this MinDF to be put in. And if it's 0.1, then it's like 10%, and so on and so forth. Okay. Now, with that in mind, what's happened in the convectorizer? You'll only get certain words by making this sort of a cut, right? And then after doing the convectorizer, you're going to do the naive-Bayes. And remember, we've done this before in homework 3. This is the idea of a pipeline. So what we're going to do out here actually in this lab is kind of deconstruct that pipeline and run it by ourselves, just to see how it goes. But you could use the pipeline machinery in scikit-learn to do it as well if you wanted to do this. But basically, there is a pipeline, and each stage of the pipeline has these parameters. The first one, which is the convectorizer, has a MinDF. And the second one, which is a naive Bayes, has this alpha parameter. So also it's worth doing this because you actually see the entire process of cross-validation in its gory detail. So we're going to create a function called cross-validation score, which takes some arbitrary score function, and we'll talk about that in a second. We're going to do 5-fold cross-validation. We're going to collect the result in this result variable. And we're going to use the k-fold function, which is provided to us by sklearn.crossvalidation, which automatically creates these train and test sets in 5 folds for us, essentially. It fits it on the training set and basically runs the score function on the test set. We add that to the result, and we divide by the number of folds. So this is what we do for some combination of the parameters. So this is at one grid point in parameter space. We run this function, and it gives us the cross-validation, the average score of the cross-validation. And we could, in a similar way, get a standard deviation if you wanted. OK. So it has this little argument called the score function. Remember, if you remember that grid search CV in sklearn also had this argument called the score function that you could put in. And that's exactly what we're doing here. And indeed, we're actually going to use a somewhat different score over here. And this is a custom score function. You saw that when we were doing the doClassify function in homework 3. We had the score function, but we never used it. And we never used it because the process we went on in homework 3, where we did have an asymmetric data set, was to sort of, actually run it without a score function, run the entire validation process, get all these ROC curves on the test set, and compare these ROC curves and on test set, or compare the profits on the test set and choose something with the highest profit, thereby eating up our test set and making it useless for doing any stuff. But the truth is that you could have done all of this right in the validation set. You could have used a score function which was the profit, and you could have actually seen the profit on the validation set. Even for an ROC curve, you could have calculated an ROC underscore AUC, which is the area under the curve. Different people, when they want to sort of maximize different things, will use different scores. And sklearn provides a bestiary of scores. It will give you a precision score, it will give you a recall score, it will give you an F1 score, which are all these different scores that people use. And you should go Google these to see which situations these are sort of used in. Or Wikipedia also has some good articles on it. In our case, we're going to use something called the log likelihood. And the log likelihood is basically the probability of the data given the parameters. And it's kind of a little bit, it's not issueless, but it's kind of a little bit more robust to asymmetry and so forth than plain accuracy is. Because it's basically maximizing the probability of the data given the parameters. So it's maximizing a probability instead of just a score over here. So we'll use that one. And we set up a grid of alphas. And we set up, and these alphas roughly represent how many new sort of like counts for a word you're hallucinating in that particular document. And then you're setting up a MinDF over here. And that's the fraction of the documents in which the word must be there. And you set up a best alpha, and then you're going to go through this loop, and then you're going to actually check the cross-validation score at each point in grid space. And then you're going to find the maximum cross-validation score, and you're going to find the best alpha and DF. And they turn out to be the alpha is roughly 5, and the DF is 1 in 1,000. OK, so you do what you do, as usual. Remember that all this was done on the test set. And you can see this by looking at the fact that you're doing a make XY fresh over here on critics, and you're running this particular vectorizer, and then you are actually you're doing the score on the same set, is it? So I think there's an error in this function, actually. I'm just doing something very fast and dirty over here, but I'm actually doing it on this make XY of critics and vectorizer. But what I should have actually done is cut this critics down into a training set and a test set. So that's kind of there's a problem with there. I do it later, but I'm not making myself particularly clear, but I've actually trained it on the entire data set, and I should have just trained it on a training set. I split it later, and I should have done this earlier, and I'll fix it in the lab. So over here, what I'm doing is I'm making an XY with the best params, and this time I'm only training it on the training set, and I'm seeing how it works on the testing set. Where I found the best params from the entire set, which is not kosher. OK. So over here, but assuming it was kosher, which I will make it by the time this lab gets to you, you can see that you have a training accuracy and a test accuracy, and these are much more sort of comparable now. And so it's not as accurate as it was before on the training set at 0.9, but it's certainly better fit. We're not overfitting. And you can see the confusion matrix as well. Okay, so what's the interpretation of this thing? What I did is I actually looked at some of the words that had the highest probabilities of being fresh and some of the words which had the lowest probabilities of being fresh. And so you can see that delight, touching, masterpiece, perfect, intelligent, remarkable, rare, entertaining, absorbing, and finest all have really high probabilities, but lame, unfortunately, pointless, dull, disappointment, bland have very low probabilities of being. And actually, you'll use this. So this is the kind of sentiment analysis that you've done over here. And you're going to be actually doing this on your homework, specifically on the adjectives in restaurant reviews. It's a similar data set to the last to homework 4 data set. And you're going to do that, and you're going to use these probabilities, actually, and do all kinds of interesting manipulations on these probabilities. And there are mispredictions as well that you can look at. And you can see mispredicted rotten quotes. The plot of the Glimmer Man involves not only the family, but our evil secret government, the Three Stooges of action. I'm not quite sure why that turned out to be rotten. But over here, I suppose the arcane antique mold in the second one made something rotten. Well, you can look at this. It's kind of fun to try and figure out why any particular quote got made into what it was. So here, how can you see a specific thing? Here I can take a piece of text and transform it using the vectorizer. This movie is not remarkable, touching, or superb in any way. And ask you for the probability. Then the probability that it's a 0 is 0.01. And the probability that it's not a 0 is 0.98. And this movie is, this sentence is saying this movie is not remarkable, touching. So it's actually been given much more weight to the fact that it's remarkable, touching, and superb in the sentence. So this is a way a classifier like this can actually fail. It's doing the wrong thing over here. So one way to have actually fixed this would have been to actually get rid of a whole bunch of stop words, and not might would have probably been done. But you don't want it would have gotten rid of it. Actually, it would not have fixed this. So it just gotten rid of not. So another way to fix this is probably to do bigrams. So if you do not remarkable, then that would predict a bad code if you did bigrams. Or you could use a random forest classifier, because a random forest classifier will actually get you the interactions between these words, which the naive Bayes does not. So that's a problem with naive Bayes classifiers you should be aware of. Now, any model which gives you probabilities, like a logistic regression or a naive Bayes classifier, you have to ask yourself the question, how good were the probabilities? And to assess how good the probabilities were, you want to make a calibration plot. And a calibration plot basically looks at the predicted probabilities versus the empirical fraction. And you would expect that if it was perfectly calibrated, this would be a 45-degree line. And it sees what you get. So let's make a plot. We want something that looks like this, which is basically telling you what the probability is against the empirical fraction, and also gives you a histogram of probabilities as to how many things is it classifying at the top end, how many at the bottom end. And there's usually this kind of marginal, like boat-like structure to this to these classifiers. So what are we doing? We're taking a collection of examples, and we're computing the freshness probability for each using the CLF predict proba. Then we're gathering these into bins of similar freshness probability. So, like, bins of maybe like 0.05 or something of that sort. I mean, this has maybe 5 or 10 shown over there, but you probably want bigger bins. For each bins, you want to count the number of examples in that bin, with that kind of probability bin, like so between 2 and 0.25, for example. And then you want to compute the fraction of examples in the bin which are fresh, because you'll have the corresponding examples on the test set, for example. And you'll just say, oh, okay, like some of these were 1s and some of these were 0s. Compute the fractions that were 1. Okay? And then you're going to plot these against each other. You're going to plot something at the center of the bin, and then you're going to plot, so on the x-axis is the probability at the center of the bin. And on the y-axis, you're going to plot the empirical fraction. Okay, and you can provide an error bar. Remember that you're either saying 1 or 0, so the kind of error bar on it is going to be the binomial sampling error. That's just given by that formula there. And the y equal to x line is a perfectly calibrated thing. And in the lower plots, we just show the number of examples that we had in each bin, without putting in the sort of like the fraction. So it gives you an idea of how many examples are in each bin against the probability of being being fresh. Okay. So it's basically telling you what the distribution of the data is as well. So it's kind of like a P of X kind of thing that this histogram is giving you. Okay, so here's the code to do it. I won't go into the code, but you can look it up. And this is the calibration plot we get on this test set. And this sort of like feature, as we saw last time, is kind of standard in naive Bayes classifiers, where you have it a little bit sort of like, you know, on the top over here and a little bit on the bottom over here. So it's kind of like shrinking a little bit in this sort of direction, being a little bit overconfident at the beginning and then being a little bit underconfident later. Okay, and this is not entirely, you know, this is because we have a well-fit classifier. If this was a kind of overfit classifier, you would typically have a boat-like structure where it has a lot of things at the bottom and a lot of things on the other side, because that's what your training sets tend to look like. So this model is still slightly overconfident while making low probability of fresh predictions. But you can see that typically it's, you know, within 1 sigma of this, maybe a little bit bad over here, but like, you know, within 1 sigma off the 45-degree line. And we're generally kind of good, and it kind of gets a little bit worse over here. But that's okay. And finally, the model makes less conclusive predictions on average. The histogram the histogram over there is more uniformly distributed, with fewer predictions, as I was saying, less of this boat. Like, so it's kind of, you know, as compared to the boat, it's less conclusive, right? If this was a very, very strong boat, then you would say that it's actually moved these things kind of a little bit further away. And naive Bayes classifiers do have a tendency to get the boat because of the multiplication of probabilities. So on the whole, this is not a bad naive Bayes classifier. It's in the middle. It's being relatively blasé about whether this was a good review or a bad review. Okay. So you can improve this even further by sort of like, you know, I was talking about random forests and I was talking about word pairs. But you can add supplemental features about genres and directors and so on and so forth, which might predict that this movie was going to be fresher. And then you could do things like visualizations, printing word reviews, and visually encodes each word with a color to indicate how that word contributes. So these are some things for you to play with. We could even actually use better features. We could use TF-IDF, and TF-IDF is a kind of vectorization where you don't just do the term frequency. Because consider the following, right? So this was a hello and world thing, but say I had the word hello in almost every document. It's kind of useless for making any predictions. So if I actually multiply this term frequency by the inverse of the document frequency, so if hello was in every document and I had 100 documents and I would multiply it by 1 by 100, then I would basically make hello less important. It won't be a number anymore, but it'll be a fraction saying how important it was. And so that's what TF-IDF does, and sometimes you can get better results with TF-IDF classifiers. Okay, so that was naive Bayes. How am I doing on time? I have a bit of time. Okay. We're going to just very briefly start with clustering in the context of in the context of text analysis, because we have a little bit of LDA. We're going to use GenSim for that. GenSim is a very nice LDA library. Use Conda to install it. Do not use pip to install it, or it might actually try and replace your existing NumPy. So that's a real gotcha. Don't use pip to install GenSim. Use Conda, and it'll be much faster if you install Conda as well. So you import GenSim, and then you do the count vectorization with removing of the stop words, all the critic quotes. And then what we do is we can use vectorizer.get feature names from sklearn, which will give us the entire names. And then you can look at the vocabulary items that are there from the count vectorizer as well. And that basically gives you a bunch of key value pairs. And the key value pairs are the feature names. The keys are feature names, and the values are how many times they occurred in the documents. And then you just flip these. Basically, it's just giving you the number with the key. And you use this to create a sparse GenSim. So this is basically X over here is the sparse matrix form, and you can put it to get a GenSim form corpus. And the GenSim form corpuses are basically just they're basically what's called a streaming corpus. You just give it one document at a time, and there's a particular interface it fits. And you'll see this in the homework, where you'll make a corpus, and it's really, really simple. It's just basically a list of lists. Except that if you want to get a little bit more fancy about it, you can actually have these list of lists coming by streaming in using a Python feature called iterators. But we won't go into that over here. I just wanted to mention that in case you wanted to read up about it. The GenSim documentation actually is super good and explains this in a lot of detail. Okay, so so we do that, and then we just run the model, and we store it in the variable LDA for latent dirichlet allocation. Here we are, storing it there. And I'm running it on this corpus GenSim. I'm using this mapping ID2 words. I'm looking for 5 topics. Why 5? Well, I don't know. I have no clue about what's the structure over here. So I just put it in. And then it was about 16,000. I'm going to do it in chunks of 1,000. So it's going to do it in 16 chunks. And the reason to do this in chunks is that GenSim's LDA model uses a particular technique, Bayesian technique called variational Bayes. And it will do the model with 1,000 documents to start with, and then it will actually have some estimation of the probabilities. And it will use that probabilities as initial conditions for the next run, and so it will actually make the convergence of the algorithm much faster. We're doing it only in one pass over the entire corpus, and we're updating the model once every chunk, once every 1,000. And we're looking for 5 topics. And I'm going to this in some detail because you'll have to actually make one of these incantations in your homework. And now you print the topics, it gets out, and it gives you some kind of fraction of what the words are. I could not actually look at any specific themes of this. Sometimes you get themes, sometimes you don't. LDA is not guaranteed to give you any themes. But it's kind of nice so when you do a visual inspection of clusters and those clusters actually mean something in your head. And if they actually correspond to some latent classes. But otherwise, they're just latent factors. Remember in homework 4, we did this stuff with latent factor models using alternating least squares. It's just like that, they're latent factors. We don't know what they are. But they are apparently, over here, like 10% film and 6% comedy. Well, no, 0.6% comedy and 1% film in the first one. Then the second one is movie, film, like dozen, which isn't even spelled right. Something about picture experiences, maybe. The third one is again talking about stuff that's a little bit funny. And the fourth one is something, has stuff about comedy. So, okay, so these are not giving you the best things on this particular data set. Maybe the fifth one is stories which have a little bit more dialogue and some kind of human character to them. I don't know. But LDA will give you topics. You always want to, as in any unsupervised machine learning algorithm, you have no way of knowing whether there is some kind of loss function that you can look at or some kind of profit or something which actually gets maximized, right? You don't have a way of evaluating this. So the way of evaluating a unsupervised algorithm is there are some metrics you can use that, a particular fit has a greater likelihood than another fit and so on and so forth. But it's not useful unless it corresponds to something that you can humanly actually cotton onto, and that's what you're generally sort of looking for. So the typical tendency is to try various unsupervised algorithms, at least on text data, until it cottons onto something. In the example that Joe gave in class, it actually, I think it was a lot of papers, it actually cottoned onto the subjects. Notice that for this to happen, that you would want papers which are only about one subject. So you would want papers just about biology, or papers just about physics, or papers just about, let's say, computing or something, so that it can actually, sort of, when it's finding these clusters, it's looking for stuff in these clusters which are very close to the cluster centers. So if you have some clusters in some kind of feature space, you want some stuff which is very close by over here, so it's very dense. So the assumption is this assumption of density. And then you'll have stuff which is crossing over. And if you had stuff crossing over everywhere, then you're not going to get very strong clusters, essentially. And so in your quote-unquote training data, you do need to have stuff which belongs to one cluster or the other if you're expecting clusters. And that is probably why the GenSim is not doing the super greatest job out here, because reviews are perhaps not the best way to actually figure to infer the entire meaning of what the movie is, what kind of movie it's, and so on and so forth. I think if you actually did this on what are they called, scripts, screen writes, you know what I'm talking about. Why is this escaping me? A script is fine. The script of a movie, then you might do a better job. Okay, so last time in the Bayes lab, we talked about discriminative models and generative models. And LDA is a generative model. And with a generative model, what we're talking about is that we need to model P of x given y. It's just not P of y given x, right? Logistic regression is a discriminative model, and you get P of c given x, where c is the class. Here you need to model P of x given c, the features belonging to one class. And because of that, we can generally sort of model P of x, because P of x then is simply summation of c, P of x given c, P of c. So that's sort of like the probability of an entire document is the probability of that the document is positive times the prior probability that the document is positive plus the probability that the document is negative times the prior probability that the document is negative. That's just a simple statement of Bayes' rule. But it gives us P of x. So one of the nice things about generative models is that they can actually give you unsupervised learning. In unsupervised learning, you are looking for the P of x. You're basically over here, when you say that there are 3 clusters here, you're telling me that in this space, which over here looks like a 2-dimensional space, that I have densities which are kind of high over here, and high over here. So this is the P of x I'm trying to get at. So that's what unsupervised learning is about. It's about finding the probability distribution of the features. If you're so lucky to have classes, you're in great shape. You don't have to do anything else. But you don't always have classes, and then you go back to what we did for the alternating least squares, or what we're doing with LDA and all of this sort, is basically you're saying, oh, let's assume there are some latent factors, or assume there are some latent classes, right? And once you assume there are some latent factors, or you assume there are some latent classes, then I can write it in this particular format. Well, there is some mixing probability lambda z, and then there's a probability of having that latent factor multiplied by next rate. It's exactly the same equation out there, where this lambda z is the P of c. But the c is no more a class. It's some kind of latent factor which may or may not exist in the data. It's just a way of writing it. And then we try and do this and see whether we get a good model. So let's actually look at the heights and weights data we had before, right? And suppose the Lord came in, hit you on the head, and told you, I don't know who are the males and who are the females in this data set. And just gave you this data set. You plot the data set, and you have this kind of vague idea that there looks like some kind of greater density here and greater density here, so there might actually be 2 clusters or something like that in this data. But you don't know that are males or females, or maybe you actually don't grab at that, and you see, okay, this looks like some mess of points to me. So but suppose you thought that there were 2 clusters, and we know that heights and weights have something to do with normal distributions, and this is heights and weights on 2 axes, so this is going to be a multivariate normal in 2 dimensions. So say, okay, I'm going to model this without knowing anything about males and females. Maybe it's not males and females. Maybe it's Homo sapiens and Neanderthals. I don't know. It's some such combination. You're going to model it as 2 Gaussians, and this is the mixing fraction of the Gaussians, or the prior probabilities of being a Homo sapien or Neanderthal, being a man or a woman, whatever your combination is. Okay, so you go and you make that. And so we do that, and it's actually done for you in a part of sklearn called sklearn.mixture. It does a Gaussian mixture model, and it does it using a specific optimization algorithm called expectation maximization, which is a fun story in itself. And if you take CS181, you'll learn a lot about it, and it's used everywhere. We fit it over here, and it's again the same way. To do unsupervised learning in scikit-learn is exactly the same thing as doing supervised learning. It's the same sort of like API. Basically, you're saying I want to look for 2 clusters. And when I say covariance type is equal to tide, I'm just saying that the covariance of the 2 needs to be equal. That's not a necessary assumption. I just made it a simplifying assumption here. And I'm just going to fit it. And here I'm just fitting on all the data because I'm not testing or training or doing anything. So it's just like a fast and quick thing. And then I plot what this looks like using the plot ellipse function I'd used earlier when we were talking about linear discriminant analysis. And I get these 2 clusters. And they look pretty much like the clusters you saw in the linear discriminant analysis. And they look pretty much like the clusters you saw in the linear discriminant analysis because there are actually 2 clusters. I just smacked you on the head and made you forget that there are males and females in here. So there are the males out there and there are the females out there. And there's always some issue of some mixing going on. You don't know which over here, which ones should be put where, but that's kind of normal for a problem of this type. But you can see that you will get 2 actually fairly representative clusters. And now if you knew what the clusters came from, right? If you knew the clusters were corresponding to males and females, you could test an unsupervised algorithm because you knew the previous classes. So that's one way to test the performance or test the ability of an unsupervised algorithm, is actually let it run on quote-unquote supervised data and then just hide the labels and see if it can actually figure out the p of x by itself. And if you model things correctly, remember we talked about this, about general models have high asymptotic efficiency. If you're actually capturing the universe in a good fashion, you're capturing heights and weights nicely by Gaussians, there's no better thing to do than something like this. And LDA does this in its own generative fashion, and Gaussian mixture models do it in its own fashion. But remember, the Gaussian mixture model is completely unsupervised. Which they should also tell you something else, that we have, when we did the supervised algorithm, we had a whole bunch of these things over here and a whole bunch of these things here. But if I'd only given you a few things over here and a few things over here, you might be able to do really well because there is this density structure in this data independent of there being classes. There's a strong density here and there's a strong density there. And if I told you that two things belong to different classes, there were like 100 of them here and 100 of them there, you could do a very good job. So in other words, the expense, the amount of money or time and everything you'd have to spend training the stuff would not be very high. And this is where what's called semi-supervised learning comes in, where you're sort of basically having a certain amount of supervised data and most of it's unsupervised. And more precisely, in your likelihood that you're maximizing, there is a part of the unsupervised thing which is also put in. I might actually have a lab at the end about this. If unsupervised learning can be an extremely powerful way to actually do stuff because you just have to spend a very little time on training things. You just get your friends to do a little bit, and if there is some hidden structure in the data, it will find it. So it's something to keep in mind going forward. But you do need to know how to use the expectation maximization algorithm, and you'll see this in gory detail in CS181, and if you want to go read it up, it's all there in Bishop's book. Okay, how do you know a priori that 2 is the number of clusters? You don't. As I said, you can test it by actually bringing back the labels and testing how the density is worked out, given those labels. You could try this whole thing for 3 clusters, and you will get a fit for 3 clusters. And there are some ways to figure out that the fitting likelihood, the chi-squared per degree of freedom, is probably less in this case, and so on and so forth. There are statistical ways of saying that this density estimation is not as good as the other one, and that's a better fit. But that's all that is. I mean, if you don't know that there were not 3 classes of people, Cro-Magnons, Neanderthals, and Homo sapiens in this, then you wouldn't know what was going on. So always in unsupervised learning, in clustering, you have to inspect and see whether this makes any sense. Okay, so that's where I'll stop. So this was basically, we started off with the vector space model for text. We went on to working through a complete naive Bayes model. After working through the complete naive Bayes model, we saw the importance of calibration of probabilities, which we haven't talked much about until this point in the semester. But you should be really doing that for any classifier which outputs probabilities. And then we talked about LDA, which is a clustering algorithm that works on text, and which you'll be doing a bit of in the homework. And then we talked about clustering algorithms in general, and how basically clustering is simply estimation of the probability density of your features. And once you estimated the probability density of your features, it may or may not split up in terms of some latent factor model C, which is what it's made up of. And if you're so lucky, C may actually correspond to classes that are there in your data. And if there are classes in your data, and the Lord just smacked you on the head and hid those classes away, and then at some later point you recovered your memory, you can actually test whether your unsupervised algorithm was any good at all. But in general, you want to actually look at these unsupervised algorithms and see if their answers make any sense. Thanks.